Another integral that we can solve by substitution of the right function, a trig function in this case, they give us x equals cos 2 theta. So to work with this, to change variable, I'll need to work out dx on d theta, which is negative 2 sine 2 theta. And now I'll have all my pieces to put into here, right? I've got my x's, so I'm going to have the integral of the square root of 1 plus cos 2 theta on 1 minus cos 2 theta. Now, instead of dx, I'm going to put negative 2 sine 2 theta d theta. Now I've changed my variable, that's good. Okay, now I've got a big square root symbol here, and I want to get rid of it by turning what's underneath the square root, the radicand, that's a weird name we never use, into something that's squared so that I can evaluate the square root. Now the way you're going to do that is use the double angle formula, cos 2 theta. You can write that in a variety of ways, 3 ways, but the 2 ones that are important to us are that you could say it's 2 cos squared theta minus 1, or you could say it's 1 minus 2 sine squared theta. Okay. Now you can see that a different one is going to be appropriate for the numerator and the denominator. Here we want something that will get rid of that one. Here we want to get rid of the one, but we use a negative. So what you're going to choose, what will be most helpful, is if I choose the 2 cos squared theta minus 1, put that on the top, that negative 1 will cancel with that. Here, because I've got everything reversed because of that negative, I should choose this one, and then this negative 1 will cancel with that one, and I'll be left with a positive 2 sine squared theta. So what you end up with is a 2 cos squared theta on the top, and a 2 sine squared theta on the bottom. Those two cancel, of course. Then you've got your... I'll put that minus 2 from here out the front, and sine 2 theta, I'm going to write that as 2 sine theta cos theta, using the sine double angle. The reason why is because I anticipate that this sine will cancel with this sine once I evaluate the square root. Okay, now that negative 2 I'll leave out the front. I'm going to get cos theta on sine theta times 2 sine theta cos theta with respect to theta, and as I anticipated, those signs cancel, and then what you've got here is negative 2 out the front, and I've got 2 cos squared theta d theta. Now I can use the same identity that I used up here in order to turn this back into something that's easier to integrate, namely a cos 2 theta type angle. In this case, I'm going to get 1 plus cos 2 theta with respect to theta. All I have to do to see that is take that negative 1 and move it over to the other side. It becomes plus 1. Okay, so now I'm almost there. I can actually evaluate this integral. That one's going to turn to a theta. That cos 2 theta is going to turn to a half sine 2 theta. And then you've got your constant, of course. Now what's going to happen here? Well, I might as well stick that 2 in to get rid of that half. That's going to become just sine 2 theta plus my constant, and at this point I've gotten to where I want to get rid of my thetas and put it back in terms of x's. Now, how am I going to do that? That 2 theta there, I'll need to use a need to use inverse trig here. So if I take cos inverse of both sides within a restricted domain, I'll get that. Then what do I do with this sine 2 theta? Well, again, I'm going to consider this 2 theta as an angle within a triangle, like so, which only works within a restricted domain. 2 theta obviously has to be acute, but it will still give us a primitive function that'll work. Okay, so if I've got cos 2 theta equals x, that's adjacent on hypotenuse, and so by Pythagoras you can see that's what the other side is equal to. So if I want sine 2 theta, I want opposite on hypotenuse will just be the square root of that. So I'm going to get, said that that was negative cos inverse, and using the triangle we got this plus the constant, and that's it.